3, it can be 4, 5, 6, 7, nth number of charges. Now, how will you find out the electric field? When yesterday, all questions which we did had, plus Q was given at a point you had to calculate, right? Easy. But now if so many charges are there, how will you find out? So what you have to do, this principle, this is valid for all the particles that are present. This is not just only valid for this. So what is meant by superposition principle is, Q1 is there, I want to find out electric field at this point. This is valid for forces also. So at this, let's say electric field is this E1. All right. What about Q2? For Q2, electric field is this. All right. What about nth number of charge? Let's say Qn. So for Qn, electric field is nth. This is the value of electric field. Nth value of electric field is present, right? Now what we have to do, we all know that electric field is a which type of quantity? Vector or scalar?
Vector.
Vector. Very good, Fadil. It's a vector quantity. So net electric field, which we have to find at this particular point, it will be the sum of all the electric fields, but they are not just added. There are arrows above their head. It means they are added vectorically. All the nth number of electric fields which are present, they are added vectorically. So this is how you find out. So superposition principle is what? It's just a principle. It's not a proper law that is valid only for one type of objects or one type of charges. Principle means you make it valid for other particles also. If we talk about forces, nth number of forces are acting. So you will find out the vector sum of all the forces which are acting. So that is what a superposition principle for a system having n interacting charges. Net field at a point is the vector sum of, main point here is the vector sum of field due to individual charges. Now we have a concept of neutral point which you should see. Point at which net electric field is 0. Net electric field, how can it be 0? When all electric fields, if they are present, all the electric fields cancel each other. That is what is meant by a neutral point. Means no electric field is present. At the neutral point, when we talk about a neutral point, no force, no field is present. This is what we call as neutral point. No electric field will be present. If electric field is present, so they will cancel each out. Means net electric field will be 0. This is just a note point for all those who have forgotten vector law, that is your parallelogram law. If two vectors are representing the adjacent sides of parallelogram, their resultant is represented by the diagonal of the parallelogram. And theta is the angle between A and B. So we write R as under root A square plus B square plus 2AB cos theta. If just in case anywhere you have 90 degree, let's say electric field 1, electric field 2, they are making 90 degree. So since this cos 90, that is theta is 90, cos 90 is 0. So what will be the net electric field? Net electric field will only be under root E1 square plus E2 square. Why am I making you do this special case? Because this is a very easy case and students waste their time in writing the entire portion. So that is better. Just remember it as under root E1 square plus E2 square. Let's see some questions also. But before that, note down these points. Make the heading superposition principle. This is the principle. This is the statement. This is the principle. Note it down. See class, how to solve this question? It says that two charges plus E and plus 4E, they are placed at separation A. It means this is saying plus E is present, plus 4E is present. They are separated by the separation A. Then it says at what point on the line joining the two, net field is 0. What is meant by this? This is the neutral point. The question will not ask you neutral point directly. It will give you like this only, where net field is 0. Means neutral point. It means electric field from both the sides will cancel. Let us assume a neutral point by ourselves. We don't know what's the neutral point. Let us assume. Let's say neutral point is here, N. Let me mark, let's say the separation from plus E is X. If the separation from plus E is X, total was A. How much is the separation from plus 4E? This is X, total is A. How much is this?
X minus A.
A minus X. It would be A minus X. Total is A. Yes, we are. It would be A minus X. Now see, at this point, your electric field, because of plus E, is actually balancing the electric field due to plus 4E. So basically, your electric field. And what is the formula of electric field? Yesterday, we have studied for point charges. K Q by R square. This is what is the formula of electric field we have studied for point charges. This you people should remember. Now, electric field due to plus E will be equal to electric field due to plus 4E because this is a neutral point. Now, let's form the equations. Yes, Aliza. Aliza, can you try? KQ by R square is the general equation. I want to find out the equation at point N due to plus E. Can you try? How do we fit in the formula because of plus E till this point? Yes, Aliza.
Ma'am, give me 2 minutes.
No, keep on trying it here only along with the class. Formula for point charges, because these are point charges. Electrons we are considering, no? Electrons, protons, these elementary particles are point charges. That's why we are using the formula. See, start with this formula, Aliza. What should come first? Look at the formula, Aliza. Answer, try to answer with the class. Then only you will be able to remember. K, shouldn't K come first?
Yes, ma'am.
Then?
Thank you.
What is charge over here?
Plus E.
Plus E. Very good. So it is K into E, right? And what is the separation of E till this neutral point?
X.
X. So it would become?
X square.
X square. Very good. Clear now?
Yes, ma'am.
This is K. Charge is E divided by X square. Yes. Next, Deborah. Deborah, please try for this plus 4E at the neutral point. How will we start? K we will have. K is there?
Yes, ma'am.
Yes, K we'll have. What about the charge next?
4E.
What is the charge? Which charge is this? We are calculating because of 4E.
A minus X.
That is the separation. Charge KQ. 4E. 4 times the electronic charge, no? See the way here the charge was plus E. These are the two charges which are present. So this will become 4E. And which you were mentioning A minus X. A minus X is the separation. So it will become A minus X whole square. So KE will get cancelled. Let's do one thing. Let's take the root because these are present. No? So that becomes 1 by X is equal to 2 by A minus X. So let's cross multiply. A minus X will be equal to 2X. A will be equal to 3X. So what is the value of X? X is a divided by 3. This is the value of x we have, right? This is the value of x we have. Now see, if this part is a by 3, we have obtained the formula a by 3. Sometimes in the question it is specified, like here it wasn't specified, find out from which charge. If it is specified, now what will you do? Suppose the question was find the neutral point from 4e. How will we solve now? See, if total is a, this was x, and now we know the value of x. X is a by 3. If total is a, this is a by 3. So this will become a minus a by 3, that is equal to 2a by 3. So whether the question is asking you from this point or this point, you all are already prepared. This is, let's say this is a point, let's say this is b point. So whether it's a point, charge at b point, this is how you will calculate. This is 2a by 3, this is a by 3. Note down this. Before that, just one more thing, class. This is a very easy portion. You should just have this in your mind. If the symmetrical system is present, just in case the symmetrical system is there, like before this, this was unsymmetrical, plus e and plus 4e. Let's say this is a symmetrical system. So at the center of a symmetrical system, the net electric field or net electric force, both of these become 0. Like a triangle with all the charges equal. Even if there becomes a 4e and here 3e, then this is not symmetrical. Symmetrical means sides are same. This side is equal to this side, as well as the charges are same. So net electric field at the center is 0. Similarly, for a square, net electric field at the center is 0 if all the sides are same and all the charges are same. Similarly, for a pentagon, E net is equal to 0. Keep on increasing the size. Net field at the center of symmetrical system will always be 0. And all these lines extend. Ultimately, these will lead to a circle. So at the center of a circle also, you will have net electric field 0. Especially people who have to appear for their entrances, for you, this technique is very important. Otherwise, in board exam, nobody will ask you separately. You have to prove it in the exams. But keep in mind the answer. Answer would be 0. Now note it down. Yes, class. So here we have to find out the electric field at point O. Now you will see how superposition principle is applied. This is a very good question, a very good example of superposition principle. And this is a very important question. This gets repeated a lot in your previous year's papers when you will see whether it's your actual CBSE board exam or whether it's your school exams. These types of questions have repeated a lot. So this is a very basic question. 4 charges are there, plus Q, plus 2Q, minus 2Q, minus Q. Point O. Point O means this center is point O. Now, this is not a symmetrical system. Otherwise, our answer would have directly been 0. We wouldn't have calculated anything. So we want to find out the electric field at this point O due to this, then due to this, due to this, and due to this. We do not have the separation. For the formula, what is the formula of electric field? K Q by R square. Do we have the separation R square? We do not have. What we can do? See, this is a bigger triangle. This is a right angled triangle. What can you do? Use Pythagoras theorem. See, look at this triangle. This side is A, this side is A, this side is unknown. So what would this AC or this AD, AC or AD both, this will be equal to under root A square plus under root A square, the diagonal. So that becomes root 2A square, or we can say A root 2. Now half of it will be what? Half, because we do not need the entire length. We need the separation from the charge to the point O. So that is half of it. So AO, or this separation BO, or this separation CO, or this separation DO, all these will be equal to A by 2 divide A root 2 divided by 2. So which is equal to A by root 2. So what do we have now? This separation with all the charges, this separation has now become A by root 2. So now we know the separation from the point of calculation to the charge. This separation we are aware of. Now K, we already know 9 into 10 to the power 9. Charges are already given. R, which was missing, we have found. Now let's calculate the individual charges first. Electric field on point O because of plus Q, that is A point. What have we studied regarding? Yesterday only we have studied, and even to you, Majid, also have told you also that for positive charges, electric fields are always away from the point. So if this is the point, if I move like this, that will be towards the charge. So away from the charge would be this. This is EA. This is electric field EA. And how to write its magnitude? Electric field EA, its magnitude. See, K is constant. What is the charge present here? Charge is plus Q. So this becomes Q divided by R square. What is the separation from point O? The separation is A by root 2. So this becomes A by root 2 whole square. This can be written as root 2 into root 2 becomes 2. It will go up KQ by A square. Coming to this B point. Before the B point, no, let's solve this C point. Look here. For the C point is a negatively charged particle, minus 2Q, minus sign. For negative charges, we move towards the charge. So if I move like this, that will be away from point C. If I move like this, that will be towards point C. So that is EC. What is the magnitude of EC? Fadil, can you try now? This EC at the point O, I want to find out this.
The electric field, ma'am.
Yes, the electric field. This is the general formula. You start, I'll help you.
Yeah, so E for C will be equal to K into minus 2Q upon A by root 2 whole square.
Very good. Just one mistake, we take the magnitude. Okay, so not minus 2, we'll take 2Q only.
Oh, okay, yeah.
Okay, rest everything was fine, perfect. Very good, Fadil. So this becomes K into 2Q divided by A by root 2 whole square. So again, this root 2 into root 2, this will go up and which will get multiplied to this 2. So that becomes 4kq divided by a square. So we have what? We have this branch. This has a EA and this has EC. Fine. Now, class, one thing. They both are in the same direction. Why not? Let's solve this branch, EA and EC. Let's solve them and have a final answer towards this side. So what will be EA plus EC? Because they are in the same direction, you can add them directly. So this becomes 2kq by a square plus 4kq by a square. That becomes 6kq by a square. So finally, this branch, EA plus EC, let me call this as E1. E1 I have got, whose value is 6kq by a square. So this is solved, which I am calling it as E1 right now, pointing towards C. Come to point B, which was left. Again, this is a positive charge, so we'll move away from.
Excuse me, ma'am.
Yes, Fadil, sir.
Sorry to interrupt, but why are we adding the two charges, the two electric fields?
We are adding the two charges because see here. If one vector is in this direction, another vector is in this direction, means they both are parallel vectors. So what do we do? Even if I just tell me, if I'm telling you 1 Newton of force is acting in this direction, another Newton of force, 2 Newton forces is acting in this direction. So what will be the net force according to you?
3
Newton. Right.
3 Newton, yeah.
It will be 3 Newton that is acting towards this side. But if the same thing happens, I'm telling you 2 Newton is acting here, 1 Newton is acting here. Now what will be your answer?
1 Newton.
1 Newton. 1 Newton towards this side because this has higher magnitude. So what did we do? Here the angle is 0 degree in parallel case. When you put it in the formula, no, under root a square plus b square plus 2ab cos theta. What happens? Cos theta is 0 degree. So cos 0 becomes 1. What are we left with? Under root a square plus b square plus 2ab. Just what is this identity? A plus b whole square under root. So under root and square get cancelled. What are we left with? Just a plus b. Right?
Okay.
If these vectors are in opposite direction, we take the angle as 180 degree. So this becomes -1. So wherever this sign was plus, this becomes minus. This sign becomes minus. Then again, this sign becomes minus. Then a minus b whole square, it becomes square get cancelled, you get a minus b. So whenever two vectors are in the same direction, we add them. Whenever the vectors are in opposite direction, we subtract them. Actually, we are following parallelogram law only. But since the angles are 0 degree and 180 degree, we are eliminating it. Now clear?
Yes, ma'am.
Okay. So yes, this was EB. What about D charge? This is negative, so I will move towards it. So this becomes ED. Now again, I have to write the magnitude of EB. Phia. This is the charge, this is the point. Can you tell me the electric field? Direction I have already told you. Yes, Phia, try. This is the general formula KQ by R square.
Can you repeat it?
Electric field at the point O because of this charge at B point.
Yes, ma'am. It will be K.
K, right? Then
K 2Q
2Q
by A by root 2 square.
Whole square. Very good. This separation is also A by root 2. So yes, we'll have value of EB right now. We are focusing. So K charge is 2Q divided by A by root 2 whole square. So this again becomes 4KQ by A square. Fine. Coming to this charge D. This D point we are having. Hafsa, can you try Hafsa? For this point.
Yes, ma'am.
KQ by A by root 2 whole square.
Whole square. Very good. K is the constant. Charge is Q, minus sign. We do not take in electric field and electric force. We just take the magnitude. So KQ and divided by what's the separation? The separation we have earlier only figured out that OD is also A by root 2. So it's whole square. Very good. So EB and we were left with ED. So that became KQ by A by root 2 whole square. So that becomes 2 KQ by A square. So which branch is this now? See, this was EC and ED. Now we have to solve them also. Two vectors acting in same direction. This is given by just addition of the two vectors because angle is 0 degree between them. So when we add them, now we can easily add these two vectors. So EB plus ED. Let me name this as E2. Why E2? Let me call the final resultant this as E2. So this becomes 4KQ by A square plus 2KQ by A square, which is 6KQ by A square again. Now, we have still not got our final value of electric field. We still have two values of electric field. One is E1, one is E2. What is E1? E1 is this. And what is E2? E2 is this. See, always remember the diagonals of the square, they are perpendicular bisectors of each other. It means this angle is 90 degree. So which means the angle between them, this is 90 degree. Two vectors acting at 90 degree. We have discussed this. Because cos theta is 90 degree and cos 90 is 0 degree, 0. This term becomes 0. So what are we left with? Under root A square plus B square. Yes. So what are we left with? Final answer. See, let me write the entire thing. Even if you write the entire part, E1 square plus E2 square plus 2 E1 E2 cos 90 degree you will have under root according to parallelogram law. So this becomes E under root E1 square plus E2 square because this entire term will become 90 degree. So see, both the magnitudes are same. This is also KQ by A square. This is also KQ by A square. Let me write it as E. Both are the same. That becomes E square plus E square, which is 2E square. So the E can come out of the bracket. We are left with E root 2. And what is the value of E? Electric field is 6 KQ by R square. And this root 2. This is the net value of electric field. Tell me, class, this question is clear to all of you? Aliza,
Yes, ma'am.
Majid?
Yes, ma'am.
Okay, class. Note down this question. In whichever part you people get stuck, you can always unmute yourself and ask. You can text me in the chat column. Try to solve this on your own. Wherever you get stuck, look up the screen and then solve. See, in the last step, no, why we have written root 2? It's under root 2 e square. Right? This is also e because this is 6kq. It's like you can write it down as under root 6kq by r square plus under root 6kq by r square. So that would be 2 times 6kq by r square. So root 2 comes out because everything are in square. Do you understand? This is under root 2e square. Under root e square is equal to e. So that's why I have brought it out. And under root 2 is left. And whatever was the magnitude, ultimately I have kept it. 6kq r square we were getting for both of the values of E1 and E2. It's clear for you now? Okay. Done, everyone? Just text me done
Yes.
if you all have completed. I want to start electric field lines with you. I hope nobody is writing. Done. All of you have completed. Okay. Electric field lines is a short topic, and it's a very light topic. And a single question only comes from electric field lines that write down the properties of electric field lines. So let us just discuss this electric field lines. So electric field lines, let me start with all of you. Superposition principle is over. These types of questions are only present in superposition principle. Now, electric field lines is a very simple topic. This is just a geometrical and pictorial representation of electric field. How can you represent electric field? What have we studied? We have studied that there, whenever charges are present, around the charge exists a space. But now, how can you see the space? You can just experience it when you are bringing another charge. If you do not have the charge, even if you are having it, how can you actually give the physical proof of it? How can you represent it? So that's why we have the concept of electric field lines like this. If I draw this, so this will tell you, suppose these are electric field lines present like this, I'll tell you. Then you'll be able to imagine it. Yes, from plus Q to minus Q, or there are lots of charges, electrons, protons kept in between that is making up this electric field line. These actually do not exist. In reality, you have just electric field, but we all need some proof, some physical existence, no, for our calculations, for our studies. Otherwise, if we just keep on imagining it, how will we represent it? So suppose this is the path of electric field. I want to find out what's the direction of electric field. Best method is drop a tangent. And these are actual, electric field is an actual thing, but pictorial, just a pictorial representation, how electric field is traveling. If I am saying this is a plus charge, so I can make electric field line like this. So you all know now that this line is moving away from it. So that will help you tell, no, that electric field line is away from the positive charge. If I just tell you this is a positive charge, yes, field lines are moving away. You cannot see, but field lines are moving away. So with our calculations, how can we show it? Because we have to give exams, we have to write everything in our studies. And for understanding also, we have to have certain pictorial representations. That is what is meant by electric field lines. And that's why we have the concept of it. Now, just to remember electric field line, certain properties are there. You just have to go through all the properties. It's very easy. It's not very difficult. Now, first point, electric field's direction is given through a tangent on electric field. And this, I think I have mentioned also. Suppose this is an electric field. This is electric field which is going. So to represent electric field line, you drop a tangent. Tangent is just a perpendicular drop to the periphery of a circle. Suppose I am saying this is an electric field line. It means electric field must be curved to this path like this. Next point. Yes, this is very important thing. See, since it is a tangent, suppose, let me tell you, this is one electric field. All right, this is one electric field. This is one more electric field. Two electric fields are crossing each other. Now, what will be the direction? What will be the direction of electric field for the electric field line? Yes. See, this is the electric field line 1. Not 0, not 0. Why 0? This is electric field line 1. This is electric field line 2. What did I tell you? Electric field, it is tangent on it. Tangent to this point would be this. And tangent to this point, I'm calculating it for here. See. If I drop a tangent, this will be the direction of electric field due to 1. And when I drop a tangent on this, this is electric field due to 2. Can you see at this point only, there are 2 different directions of electric field, E1 also and E2 also. There has to be only one electric field in your system. If 2 electric fields intersect, they will give you 2 different directions of electric field lines like this. One direction here, one direction here. That's why 2 electric field lines can never intersect with each other. They have to be at a separation so that their tangents also never meet. And for the same electric field line, you do not have 2 directions. Right? That's why, because see, at a single point 2 electric fields are present, which is physically impossible. In class 11th, you people must have studied that lesson, fluids, mechanical properties of fluids. There, you must have studied in hydrodynamics, turbulent flow, streamline flow, laminar flow. Are you able to recall? So if you remember, if any one of you remembers this, 2 streamlines also cannot intersect because at the point they give directions, 2 different directions. So a very similar case is this only regarding electric field. This then this is the first point regarding tangent and how cannot they intersect. Nextly, if electric field lines are present, wherever you see, let's say this is electric field line 1, this is electric field line 2. Wherever the electric field lines are closely located to each other, see the separation is very small. Wherever electric field lines are located close, it means it is telling you that the electric field in that region is stronger. And wherever they are far apart from each other, like this separation is there. See, this separation is more. That tells you electric field is weaker in nature. So by this figure, this example, you can take an example that E1 is stronger than electric field 2. If 2 field lines do not intersect, then how can we say that a neutral point, the electric field cancel each other? Because see, neutral point, that's why this is proving the existence of neutral point. At the neutral point, electric fields are cancelling each other. This doesn't mean that there are 2 electric field lines which are passing through each other and they are cancelling each other. At a neutral point, this is suppose 1 charge, this is 2nd charge. This is 1, Q1, this is Q2. This charge is generating certain electric field here. This charge is generating certain electric field here. At this charge, because of different charges, there can exist so many field lines. But only for a single charge, you can have only 1 electric field. So for this charge, at this point, you can just have this direction. For this positive, this will be just this direction. For this, there will be no other direction present. This is because of this. One more can be there because of another charge. But for a single charge, you are having single direction of electric field only. Right now, what is happening in the intersection part? See. In the intersection part, what is happening? These are the electric field lines generated from the same charge. At this point, no, when the electric field lines are crossing each other, here will be 1 single charge present. So this charge will be having this direction and this charge will be having this direction. So for the same charge, how can you have 2 directions? Now clear, Fadil? Okay. Yes, so I was telling you regarding this only. Rest of the points, let's do it later. First, note it down from you. It is for same charge only, because when we are talking about this point, here only one charge is present. Right, we are talking about this charge. Two electric field lines can cross each other, but they cannot intersect. Crossing means they are actually not intersecting. They are just passing through each other. That is what happens when we talk about the neutral points and all. There are different electric fields are just present. They are not actually intersecting with each other. It's just for our references we draw. Intersection means they are actually crossing each other like this. So this is valid only for a single charge. For single charge, two different directions are not present. If different charges are present, different electric fields will be there. Yes, class, the next property, see, it's regarding the electric field lines. So what have we studied? For positive charge, we move away from the charge. So that's how you will depict an electric field line. See, all the charges for positive charges, we are moving away from the charge. So always remember, and for negative, you will move towards the charge like this. For the negative charge, you will move towards the charge. This is what we had studied regarding electric field. So same thing will be regarding electric field line. If you have positive charges, simply move away from the charge. If you are having negative charges, simply move towards the charge. But what if they both are kept together? Right now, they both are separated. Suppose if both the charges are kept together. This is positive charge, this is negative charge. So what have we studied? For positive, field lines move away, and for negative, they move towards. So away for positive, towards for negative. See, away for the positive charge and going towards the negative. Again, away from this, going towards it. So all the field lines which are present for the positive charge, these will be moving away. And for all the field lines for the negative charge, they'll be entering like this. This is how, and this is a set of positive and negative charges called a dipole. We have a separate section on dipole, there we'll study this. But right now, just make these diagrams. So what it's written, electric field lines originate from positive and terminate at the negative charge. Fourth point is electric field lines are continuous curves. Continuous curves means you have seen. I'm not drawing it in dotted manner. No, you draw it continuously. This is what is meant by a continuous line. Fine, note down this third point and fourth point as well. Yes, class, all those who have written till the fourth point, just text me done in the chat column. Rest of the portions we'll complete it in the next class. Because few points are only left, electric field line is almost over. So now very small topics, dipole moment and torque, these are small topics. Electric flux is a big topic that we'll discuss in the next class. So next weekend, we'll finish off with this lesson. But please attempt the after class assessment. So I'll also have an idea how much you people have understood. And if you have any doubts, you can let me know. All right. So thank you so much, class. Let's meet the next weekend. Thank you so much.
Thank you, ma'am. Excuse me.
Yes, Fadil, say.
Ma'am, till when are the after class assessments available?
After class assessments are just available for half an hour.
Okay, okay.
Okay. Okay, so that, see, the actual, no, earlier we used to have the duration of the class as 2 hours, but then extra time we would use for these after class assessments, for these tests and all. So what now we do, we just have the teaching part for 1.5 hours, and that half an hour, so that your class is of 2 hours, that part we devote in after class